In Chapter 16, we're going to study thermodynamics. Thermodynamics looks at the relationships between energy and work and allows us to predict if certain chemical reactions and physical processes will actually occur under certain conditions. So it gives you some predictive ability to be able to determine if a reaction will actually take place. Before we jump right into thermodynamics, we want to review what we've learned previously in General Chemistry 1 about energy, such as the first law of thermodynamics, what internal energy is, delta U, pressure, volume, work, and enthalpy, delta H. The word thermodynamics can refer to a few different types of processes. We're going to focus in on chemical thermodynamics, which is the study of the role of energy in chemical changes and the spontaneity of chemical processes. The word thermo means heat, and the word dynamics means movement. So usually we look at how heat flows into a chemical reaction to take place, or a chemical reaction can generate heat as an exothermic reaction. Based on a few laws that summarize centuries of experimental observation, we can look at laws that give us the relationship between energy, work, heat, and temperature. We previously learned about the first law of thermodynamics, which is also sometimes known as the law of conservation of energy. The first law states that energy can be transferred as heat or work, but it cannot be created or destroyed. So energy can only change forms. The internal energy of a system is the system's total energy. It's the sum of all the kinetic and potential energies of the particles. Delta U, or the change in internal energy, can be calculated by taking the internal energy of the products minus the internal energy of the reactants. If delta U is greater than 0 or positive, that would mean energy would be flowing into the system. If delta U is less than 0 or negative, it would mean energy is flowing out of the system to the surroundings. To think about internal energy, let's compare systems at the exact same temperature: a monoatomic gas, a molecular gas, and something that would be like a liquid or a solid. An example of a monoatomic gas could be something like gaseous neon. Neon is just simply one element, so it would be monoatomic. All it would have translational kinetic energy. So neon can move around, but it's not going to have any intermolecular forces. A molecular gas could be something like carbon monoxide. Here we have carbon triply bonded to oxygen. So along with that translational kinetic energy, that gas would also have vibrational and rotational kinetic energy. It can move around, but the bonds can also vibrate between carbon and oxygen. So it will have a higher internal energy than something like a monoatomic gas. Lastly, liquids or solids have the highest internal energy. Imagine we have water and we have H2O. The potential energy from the intermolecular forces is what mostly creates that higher internal energy. We know that something like water will have hydrogen bonding due to having a hydrogen bonded to a highly electronegative atom. So having that extra intermolecular forces that gases do not have, solids or liquids have much higher internal energy. Energy can be exchanged in two ways. Heat can be absorbed or released. The symbol for heat is lowercase q. Work can be done on or by the system. The symbol for work is lowercase w. The internal energy is the net change in energy when we look at the change in heat plus the change in work. We use different signs to indicate if work is being done on or done by, or if heat is being absorbed or released. A positive sign for Q means that heat is being absorbed by the system, whereas a negative sign for Q means that heat is being released by the system. A positive sign for work means work is being done on the system, and a negative sign for work means that work is being done by the system. So when we take the sum of all the heat and the work changes and we plug them in to this formula, that'll tell us the internal energy change. An important type of work is known as pressure volume work. There are two types of work in chemical systems: electrical work, which is the focus of Chapter 17 over electrochemistry, and expansion-contraction work, which is just another name for pressure volume work, or PV work for short. Pressure volume work is important when discussing gases. Gases change the volume substantially, and so a change in volume contributes to work being done by the system or done on the system. That work can be calculated by taking negative P, which is the external pressure, times the change in the volume, which is delta V. Changes in the volume of gases are what is going to primarily cause pressure volume work to occur. So if we look at the picture on the right-hand side, we have an initial state and we have a final state. And there's some external pressure pushing down on our system. We can imagine our system as a chemical reaction taking place. From the picture, we can see that the system has pushed back against the surroundings and the volume of the system has expanded. In this case, the system did work on the surroundings. And since the system did work on the surroundings, the work would be a negative value since the system did that work. We can combine the concept of pressure volume work with that of internal energy. The internal energy change could be calculated by looking at the sum of the heat plus the work changes. And we just said that work could be calculated by taking the negative pressure times the change in the volume. So we can substitute that negative P times delta V in for W. That gave us delta U is equal to Q plus negative P times delta V, or Q minus P times delta V. If we have a container that has a fixed volume, we can also set delta V to 0 because that term will not change. V final and V initial will always be the same if it's in a fixed volume container. So that takes our whole P times delta V term away if that delta V is equal to 0. That just leaves us with delta U is equal to Q sub V. And that sub V tells us that we're at constant volume. If we're at constant volume, that means that the entire energy change must be given off or absorbed as heat, since no volume changes can occur. And what that formula delta U equals Q sub V means is that internal energy is heat change at constant volume. That's how we could actually measure the internal energy of a system. Often a special device known as a bomb calorimeter is used to measure internal energy changes. You might remember previously learning about a special device known as a bomb calorimeter. The bomb calorimeter can measure heat content at constant volume, or in other words, the internal energy of the system. The sample would be placed inside of the bomb where it is combusted. The temperature of the water is measured before and after the reaction to determine how much heat is either released or absorbed from the reaction. But since the sample's in the bomb, volume changes cannot occur due to it being heavily insulated. Many chemical reactions take place in containers that are open to the atmosphere under constant pressure rather than at constant volume, which is where we learned about a topic known as enthalpy. Enthalpy is abbreviated with a capital delta H, and it's the heat change at constant pressure. Delta H can be calculated by taking delta U, or the change in internal energy, plus the external pressure times the change in volume that could occur. Delta H is abbreviated as equal to Q sub P, where the sub P means constant pressure. Enthalpy reactions are carried out on an open benchtop in something like a coffee cup calorimeter, which gives us a system that cannot exchange heat with the surroundings. We're trying to keep all the heat inside so we can measure the change in temperature that occurs from a reaction. If we measured a delta H and we got that it was a positive value, that was said to be endothermic. If we measured the enthalpy and we got a negative value, that was said to be an exothermic reaction. Endothermic and exothermic reactions are important to understanding thermodynamics. Next, we're going to learn about spontaneous processes. Spontaneous processes have a natural tendency to occur in one direction given a set of conditions. A spontaneous change is one that will occur by itself without continuous outside assistance. So for example, if we have a gas and it's separated by a valve, and we were to open that valve, the gas would spontaneously flow into the other side that is a vacuum. It has no gas particles in there, and so they will start migrating to the other side until they are essentially equally distributed between the two containers. If we were to think about, would this reaction or process go in the opposite direction? Will the gas particles ever move back to one side and leave one side empty? They will not. It would be non-spontaneous in the reverse direction. Spontaneous change always moves towards equilibrium. And if a reaction is spontaneous in one direction, it will always be non-spontaneous in the reverse direction. Spontaneous does not equal fast. The rate of a reaction depends upon the chemical kinetics, not if it's thermodynamically favorable or not. An example of a spontaneous but very slow reaction is the conversion of diamond into graphite. Diamond and graphite are both different allotropes of carbon, which essentially means that the atoms are just arranged in different ways. Diamond will spontaneously start to change into its other arrangement of graphite, but it happens at such a slow rate that we don't have to worry about any diamonds decomposing in front of our eyes throughout our lifetime. But it is spontaneous, meaning that graphite is more thermodynamically stable than diamond is. So it changes into its more stable form over time. But the kinetics tell us that it's such a slow process that we don't have to really worry about it overall happening and losing our diamonds. So two things that are really important when learning about chemical reactions are the thermodynamic stability and the kinetics of the reaction. When we previously learned about kinetics, we learned that the rate of a reaction will mainly depend upon the activation energy of that reaction. So the activation energy was the big barrier that was the difference in the reactants reaching the transition state for that reaction. So the larger that energy barrier is, the slower the reaction is going to proceed. So the kinetics determine the rate, not the thermodynamics. A non-spontaneous process or non-spontaneous change is one that can only occur if external work is done on the system. So if you imagine you have a glass of water sitting out, you've never spontaneously seen water decompose into hydrogen gas and into oxygen gas. It never breaks back down into its elements on its own. But that doesn't mean that we can't drive a non-spontaneous process forward. It just is going to require an external source of work to push it forward. So water can undergo electrolysis through the use of a battery. We can push energy into that in order to break the water back down into hydrogen gas and into oxygen gas. This chamber would represent the hydrogen gas being formed, and this chamber would represent the oxygen gas being formed, since we form 2 moles of hydrogen to every 1 mole of oxygen. So there would be more hydrogen gas than oxygen gas being formed as that water decomposes back down into its elements. So a spontaneous process occurs naturally in one direction, but we can drive non-spontaneous changes forward by providing that external work. Many spontaneous reactions are also exothermic reactions, which means heat flows out of the system to the surroundings. An exothermic reaction means that the energy of the products is lower than the energy of the reactants, meaning that the products are more stable than the reactants since they're at a lower energy. It was once thought that all spontaneous reactions were exothermic or had a delta H that was negative, but that was proven incorrect. There are also spontaneous processes that can be endothermic as well. It's easy to understand why an exothermic process would also be spontaneous. The products of an exothermic process are at a lower energy than the reactants, so the extra energy is released in the form of heat, and we're moving from a less stable state to a more stable state. But an endothermic process is the exact opposite. In this case, this reaction requires energy to proceed. It does not release energy. So it's odd that there are endothermic processes that are also spontaneous. So there must be something else that we have to consider for an endothermic reaction to occur spontaneously. An example of a common endothermic reaction that is also spontaneous is solid water or ice spontaneously turning into liquid water at room temperature. We could talk about the enthalpy of fusion, which is the energy required for this process to take place, this phase change. Heat is gained by the system from the surroundings in this endothermic process. The block of ice will gain heat from the room, essentially, from its surroundings. It'll absorb that heat and it will change into liquid water. So for this to occur, it has to absorb energy, not release energy. So this means that our ice is actually at a more stable state than our water is. So we need to learn what is going to account for this spontaneous endothermic process to occur. The new thermodynamic property that will help us decide if a process is spontaneous or non-spontaneous is known as entropy. The change in entropy is abbreviated as delta S. Entropy is disorder or molecular randomness that has to do with the orientation and distribution. Nature will always move towards maximum randomness or maximum entropy, where disorder is favorable. Entropy is a state function, so we can only know the final state and the initial state to calculate the change in the entropy. Values for delta S can be positive or negative. The entropy change accounts for spontaneous processes that are also endothermic or have a positive delta H. Imagine that we have a solid on the left and a liquid on the right. The solid particles are packed closely together and they're highly ordered. A substance that is highly ordered has low entropy or low disorder. If a solid substance turns into a liquid, now the particles are free to move around a little bit. They have a higher disorder to them and therefore a higher entropy. So as we move from a solid to a liquid to a gas, we're increasing in disorder and increasing the entropy of the system, which is favorable. Simply viewing entropy as disorder is a little bit of a simplified view of it. 9 times out of 10, the view of entropy as disorder will work well for our class. If you take any advanced chemistry, though, you might want to understand entropy a little bit deeper. The entropy has to do with how many microstates or how many ways you can distribute energy amongst the molecules of a substance. If we imagine we have a reaction of A going to B, reactant A has energy in multiples of 10. Product B has energy in multiples of 5. Let's say that our total energy of 3 molecules or 3 particles for each of them must equal 20 units. So how can we distribute the energy for reactant A if the energy comes in multiples of 10 to get it to add up to 20? So we could take 1 particle and place it right at 20, and the other 2 particles out of the 3 could be placed at 0. We could take 2 particles, each of 10, and place them at 10, and 1 particle and place it at 0. Those would be the 2 configurations or the 2 microstate ways that we could distribute the energy for reactant A. But B has energy in multiples of 5. So now there's going to be many more ways that we can distribute the energy for product B. How could we distribute the energy in order to still add up to our 20 units? We could take 1 particle and place it at 20, and then 2 of them at 0. We could take 1 and place it at 15 and the other at 5, and the last one at 0. That would add up to 20. We could place 2 of them at 10 and 1 at 0. Or we could place 2 at 5 and 1 at 10 and none at 0. All of those possible microstates or configurations would add up to those 20 units. But B would be at higher entropy than A because there's more ways to distribute that energy, which is really what entropy is. A positive value for delta S means an increase in the number of ways energy can be distributed among a system's molecules, whereas a negative value for the entropy or delta S would indicate a decrease in number of ways that energy can be distributed among the system's molecules. So a positive delta S is a good thing. It means that it's higher disorder, higher ways that you can distribute the energy, which is more favorable. Why does Mother Nature move spontaneously towards maximum randomness? This is because randomness is much more probable than having a highly ordered system. So having an increase in entropy or disorder is always going to be favorable. And spontaneous reactions will typically favor having more disorder. It is possible to predict whether the entropy change is positive or negative for a given change taking place. There are some factors that will influence the magnitude of delta S: the volume, the temperature, the physical state, solid, liquid, or gas, and the number of particles present, or essentially how complex that substance is. When looking at entropy and volume, for gases, the entropy will increase with increasing volume. There are more possible ways for the total kinetic energy to be distributed among the molecules if they're in a larger space. So on A, we can see that there is a divider separating the two sides of the chamber, and all the gas particles are contained on the left. If we remove that divider, as is in figure B, we can see that the gas particles are going to spontaneously start filling the empty side. In C, the particles are now spaced out among a higher volume. So there's more disorder amongst them because they have more room to spread amongst themselves. So the entropy has increased in going from A to C. The entropy is associated with orientation and distribution, but it's also associated with molecular motion. When we measure the temperature of something, we're measuring the average kinetic energy or the motion of those molecules. Therefore, the higher the temperature is, the larger the entropy of that substance will be. When you increase the temperature, you're increasing the average kinetic energy. At absolute zero, which is 0 Kelvin, the atoms are not moving at all. They're locked in position. There is minimal kinetic energy here. As you start increasing the temperature, the particles will begin to vibrate and have more kinetic energy, and therefore more ways to distribute that energy, so they'll start having a higher entropy. At the highest temperature, the vibration of the particles is going to be the greatest, and they will have the highest entropy. The physical state of a substance can tell you about its entropy. As we go from a solid to a liquid, delta S would be positive, signifying an increase in entropy. But if a liquid freezes to a solid, it would become more ordered. So going from a liquid to a solid would have a negative sign for its entropy. Going from a liquid to a gas or evaporation would cause an increase in disorder because the gas particles are spaced much farther apart and they have more kinetic energy. So that would be a positive sign for delta S. If a gas condenses into a liquid, it would be becoming more ordered. So that would be a negative sign for delta S. A state change going from a solid to a liquid to a gas would cause an increase in the entropy of the system. And the reverse would be true as well. Going from a gas to a liquid or a liquid to a solid would be a decrease in the entropy of the system, meaning a negative delta S. The number of particles is another way to predict whether there has been an increase or decrease in entropy. Delta S is an extensive property, which means that it depends directly upon the number of particles that are present. If we look at the box on the left and the box on the right, the left has a lesser number of particles and therefore a lower entropy. The box on the right contains a much greater number of particles and will have a higher entropy or more disorder. The more molecules there are, the more ways there are to distribute the total energy. A reaction that produces more particles will end up having a higher entropy than one that produces less particles. We can use some of the general rules to predict the sign of delta S for each of the following changes. A positive sign for delta S indicates going from reactants to products has an increase in entropy, whereas a negative sign for delta S says that going from reactants to products would signify a decrease in entropy. So in A, we have aqueous silver ions and aqueous bromide ions combining to form a silver bromide precipitate, which is a solid. The aqueous ions would have more disorder being in the liquid state than when they come together to form a highly ordered solid. So our entropy change for this process would be negative due to forming a solid. In B, we have liquid water evaporating to form gaseous water. So we went from a liquid to a gas, and a gas is going to have a higher entropy than a liquid. So the delta S for this process would be a positive value. In C, we have solid carbon dioxide going directly to gaseous carbon dioxide. This process is known as sublimation. Going from a solid, which is highly ordered, to a gas, which is highly disordered, would signify an increase in the entropy of the system. So it would be positive. In D, we have 2 moles of gaseous sulfur dioxide combining with 1 mole of gaseous oxygen, forming 2 moles of gaseous sulfur trioxide. So we have all gases as our substances. It's best to look at the number of moles of gas on the reactant side and the number of moles of gas on the product side. There are 3 moles of gas on the reactant side and only 2 moles of gas on the product side. So since we decrease the number of gaseous particles, it would be a decrease in disorder. So our entropy change would be a negative. And lastly, in E, we have 2 moles of gaseous hydrogen plus 1 mole of gaseous oxygen, forming 2 moles of liquid water. We went from 3 moles of gas on the reactant side to essentially 0 moles of gas on the product side. So this would signify a decrease in disorder, and our entropy change would be negative. Predict the sign of delta S in the system for each of the following. A, we have solid calcium sulfate decomposing into solid calcium oxide and sulfur trioxide gas. So we had a solid and we formed another solid, but we also formed a gas as one of the products, and gases are highly disordered. So our delta S change, or our entropy change for this process, would be positive because we formed a gas which is highly disordered. B, we have gaseous nitrogen plus 3 moles of gaseous hydrogen forming 2 moles of gaseous ammonia. Total number of moles of gas on the left-hand side is 4, and we have 2 moles of gas on the right-hand side. So we had more moles of gas on the reactant side than we do on the product side, so it's getting more ordered or less disordered. So we would have a negative sign for the entropy change. In C, we have solid iodine turning into gaseous iodine. So going from a solid to a gas would be increasing the disorder, so delta S would be positive. And lastly, in D, we have solid calcium hydroxide dissolving in water into aqueous calcium 2+ ions and aqueous hydroxide ions. So we took something that was a highly ordered solid and we dissolved it into ions, breaking it up into essentially more particles being formed. So in this case, it's becoming more disordered. So delta S would be a positive value.